So we stay here, we stay in this place, or do we need to log in again?
No, no, we stay in this place.
Stay
We
here.
are waiting for the number of participants to rise.
Okay.
They're coming.
You can see at the bottom the number, and it's
Mhm.
quickly getting to a
Sure.
good number. Good afternoon, all, but I won't start until the numbers rise a little bit.
Yeah.
Let's wait a few seconds for the others.
Until we reach 100, yeah, to start.
I'll start at exactly 2:01. Okay, we have reached 2:01. Good afternoon, all, and thanks once again for joining us for the last of the series of webinars on digital technology. As with before, let me just remind you about the boxes that we have. You will note the chat box at the bottom of the screen as well as the Q&A box. Please direct all your questions to speakers into the Q&A box. And the chat box should be limited for logistical issues, technological issues for us at Waterlinks and Xylem as organizers. So we're very happy this afternoon to have really two great speakers on the subject of digital technology for Asia sanitation management. We have Dora Narayana and Dr. Jörg Gebhard. I will introduce them shortly, but before that, let's understand who's in the room. Let's have a quick audience polling. I encourage you all to please participate at this poll. I'll give you about a minute and a half to complete the poll questions. There are 5. Please scroll down. Please respond to the poll. Come on. Thank you. About 30 of you have not responded. May I just request kindly that you do respond? This will help us really in understanding the audience makeup. Okay, I think we have enough responses. Okay, so just to let you all know, we have mostly male participants, 74%, mostly between the ages of 30 and 40, but those between 40 and 50 is also quite a large participation. Uh, in terms of the sector, most of you are from the government sector. So I suppose these are government public water and sanitation systems. Level of the company, very interesting, a lot of executive and mid-level, and also quite almost identical in terms of executive, mid-level, and technical. And as far as expectations go, majority of you have chosen the first one, which is to understand what digital transformation in urban water supply and sanitation operations really means. So thank you for that. I'm going to stop sharing this poll now. Okay, so let me call on our first speaker. Our first speaker is Dora Narayana. He's had over 40 years in this specific industry of sewerage, working for government, particularly IWK, which is Malaysia's national sewerage utility. He has been an independent consultant since his retirement. I'm not going to tell you exactly when he retired, so I'm keeping his age unknown for now, Dora. Since his retirement, Dora has also helped us out a lot, particular to Waterlinks. He has joined the board and has been a member of the board for a year now. He has a Bachelor of Technology in Civil Engineering from IIT Madras, India, and a graduate certificate in engineering from Melbourne University. So please, Dora, floor is yours.
Thank you very much, Mai, and good afternoon to everyone who is here, and maybe good morning to some of you. So as Mai said, my background is pretty much from utility, and also I've been with the government as well. And for a while, I've been working with people in India, Bangladesh, Nepal, and also parts of Africa on sanitation, and that's mostly on-site sanitation. So I'm going to speak about digital transformation here from the perspective of a practitioner in the utility or in local government. So you see that from the time that humans started collecting and compiling information and putting it down on various media, and until about 40 to 50 years ago, the changes were not very perceptible. So the data, instead of being on stone tablets or on papyrus, now it's on paper. But it's also a lot of the information that remains in people's head. People just remember it. So that is how it was. And of course, this has got a lot of drawbacks in the sense that they get lost or destroyed. They are not available when you need them. Retrieval is difficult. But there was nothing better available. There was no real better system available to do that. And therefore, it just continued. Then expectations change. You know, people wanted decisions to be made quickly. They wanted actions to be, immediate. And that timing of that demand that arose was coincidental with the enhanced digital capability that also came up because of technological improvements. And then the journey that followed is this. So people had this decision-making challenge of taking all this data that was available and having some kind of a data system to organize it and present it in a way where you could make a decision. And then some decision-making tools were developed. And that sort of helped them to make the decisions and move on to action. But several issues cropped up. Data was not fully available as they wanted. So there's a lot of gaps in the data. And there was also data that was not complete, or that was not reliable. So they had these shortcomings. And in that, they started to look at data acquisition. And that again costs a lot of money to acquire. So they had to make a call. Do you want to have so much data? Is it worth spending the money to do it? And then they start differentiating between what they must have and what is nice to have. Then they started developing systems to manage the data and utility applications, getting the data suitable and ready for the decision making. And of course, the final steps were the algorithms and the automation that took place that then resulted in either the decisions or the action. And this was a journey that I also went through in the organizations that I worked for. So initially, it was basically transferring the available information from the traditional media, paper, drawings, from people's memory into some kind of a digital media, scanning, digitization, and so on. And next, there were systems to acquire, manage, and transmit these informations where as required. Some analysis tools, and then linking and the integration of different types of information, different types of databases. And then it became much more easier You could search and retrieve what you wanted quickly. You could send the data to the remote locations where they were required. And there was also possibility of visualization. So you could present the data in such a way that it could be visualized. It could be easily looked at in a way that it can be, it can make a lot of sense to the user. And this is an example of a GIS map of a sewer network. And there are, as you can see, manholes and pipelines and also houses which are connected, house connections. And you could click on some of these to get attributes. You find out what the diameter of the sewer is, what material it is, and things like that. So this was a basic form of a tool to visualize the data instead of being in a table form. And then you could also have GIS in the form of layers. So you could split that information in the GIS into different layers and overlay them in different combinations as well. And these become a useful tool for planning, all right? Now, this from the silo organization of these informations, they start linking this map-based data to other data. For example, in our organization, we had asset information on all our sewer lines, our sewage treatment facilities, and so on. Maintenance information on our equipment, on our sewers, billing information, our customer complaint information, performance data. So all these databases, which were all existing in silos, they got integrated together with the GIS map and made available to different users in different formats that will be more suitable for them, right? And when we did this, we start finding the gaps in the data, that there's some information we'd like to have, and that makes information insufficient for you to make the decisions you want, right? Then there's a data acquisition stage that takes place. For example, what is happening inside the buried sewer pipe, for example. So we have a CCTV, the camera which is now sent through the pipeline to gather information. It records a video, and that information is then translated into a form which makes sense for the decision maker. So in this case, you can see there, it's a condition assessment format where you can see the red bands are where the sewer pipeline is undergoing some degradation or some cracking or some structural issues, and the green ones are those which are okay. And this makes it very easy for the person to visualize this information and make decisions from here. Then we have underground utilities, which again are hidden, and these are required for the purpose of construction and also future maintenance. Again, these are gathered from using various technologies like electromagnetic techniques, ground penetrating radars, lasers, and other things. And then a three-dimensional underground visualization is possible. It's also nowadays people are also using BIMs, which are building information models, to see an underground model of the area that we are interested in to see what is below the road, right? So these were all data acquisition tools. Then it also became possible to transmit information using wireless technologies. And that meant that unmanned sewage treatment facilities which are remote, they could be linked up with some sensors at the key locations, key processes, to a centralized control point where you could get an early warning of anything that is not working right or anything that may need some adjustment, and the team could be sent there instead of having the team there all the time. Electronic security to alert on possible people who are going in there, unauthorized entry or maybe theft. So these are also possible here. And the sewer network again has similar. So you can have a level sensor, and from there you can collect information about flows, blockages, and things like that. And over time, as we get more information about the possible problems that are happening, you can develop a heat map. And these heat maps will show the priority for preventive maintenance of your sewer network. For process control efficiencies, there are several technologies which have been used, SCADA, which are remote controls, dissolved oxygen meters, flow meters, and so on, which are able to, gather data on a continuous basis, and some process automation can then be carried out, where the algorithm to decide to adjust process parameters and so on. And real-time performance monitoring is also possible. In the case of Malaysia, we have a very large number of small sewage treatment plants which are dispersed all over. And we had come up with a risk monitoring framework using various criteria. And from there, a asset risk monitoring map could be created. And then our operational focus can be decided on that basis, that which are the plants which are most critical and which require more attention, and which are the ones which can be left to run and with some minimal supervision. And maintenance strategies, preventive, predictive, and even now prescriptive maintenance is possible based on the parameters which are being measured. And our CapEx plan can be adjusted to give the maximum impact to the performance of the asset portfolio. Customers are also linked to the assets. We know which customer is linked to which part of the sewer line and to which sewage treatment plant. And that enables us to have a better communication with the customers in the event of any breakdown or any problems that are happening that are likely to affect that customer. The communication could be sent to the concerned customers, and some preventive methods could also be carried out. Our billing strategies could be improved. So this has helped by having this method of linking customers to assets. And this was an initiative that we carried out. We all have heard of non-revenue water, but we called it non-revenue customer. And these were customers who were receiving service. They were connected to the system, but they were not in the billing database. So a GIS system of the service area overlaid with the customer database can identify which are the customers who have been left out of the billing process. So this resulted in many millions of unidentified customers being billed, and the revenues were quite substantial as well. And we have now also included service request systems where customer complaints, customer service requests, they are routed through a call center, and from the call center, automated work orders are sent to handheld devices which the work teams at the respective sites are holding. And the workflow of approvals of those processes, as well as any resources that are required, manpower, materials, and so on, are also done online through that system. There is also a process of escalation, where when this problem is not solved within the allowed time period, then it escalates to the next level and so on. There is a feedback or closure loop again, where the customer is informed when the problem has been resolved. And also from here, the history of events that are taking place in that particular asset or in that particular sewer network, for example, that is also being compiled. And this can be used for the purpose of planning of future maintenance strategies. Plan submissions for approvals has also been, this is now in the process. Online approvals are being introduced where you don't need a paper submission, but this can be done online. And this is, of course, much faster and easier. And there is also reduced interaction between the submitting person and the personnel involved. So there is a transparency and integrity which is enhanced here. Moreover, the process, the dates of submission and the processing, these are all available to the public, and the public is able to view the status of their application, and that becomes a very much more transparent process. And of late, for large projects, submissions are also in the form of building information models. So these BIMs are three-dimensional models which are submitted, and those become a permanent record for the assets and can be utilized throughout its lifetime. Other things that the utility did was also, of course, communications, which traditionally had been through newspapers and TV and so on. Now they started using Facebook and other Twitter and other social media to reach out to people. It was much faster, much more effective. For procurements, systems like e-bidding and e-auction, these have been put in place where the contractors and vendors are registered and they're able to put in their bids over the system. And evaluation, approval, and awards are also being done through that. And finally, all this information that is being gathered is now able to be organized, and there is a knowledge repository which has been created in the form of the intranet within the company for dissemination within the company, as well as some of the information which are for public consumption. It's able to be disseminated through to the public who are interested. So basically, the benefits are many. I think these have become very obvious. And those which are monetary are, of course, cost reduction and revenue enhancements. But the intangible benefits are the customer experience, that people see a much better service, reliability of the assets and performance. The people, the working people, we are able to move to a higher expertise rather than people doing menial tasks. So a lot of the menial tasks and the paperwork, these are being reduced. And of course, there are regulatory compliances which are enhanced because of the oversight is able to be done by the regulator through the systems as well. Now let's look at, all this while we are looking at what the utility did, which is pretty much on the sewer systems. But what's predominant in most of the world is the on-site sanitation systems. These are the ones which the bulk of the world in Asia and Africa are using. And what digital transformation is possible for these? Now, the problem with this is that this is at a more basic level because there are very few utilities which are running this on-site system. There are, but not many. And mostly these are local authorities which are running these systems, managing them. And they are not strong financially or in terms of capacity. And often there is no drive, and they are very dispersed, right? They are small, so they're dispersed, though there is no real drive to improve how they are doing things. So this has faced a handicap in that particular way, but still some improvements have taken place. For example, here, this Sanitation, which I've shown at the bottom of here, is basically a app-based thing which works on a phone, and that is used for service assessment in cities, information gathering. And that information gathered, the system is able to carry out some analysis and presentation in the form of maps and so on. This was developed by a particular partner of a donor agency in India. And the other one on the left, you can see, this is called a Velyzer. This was used in Africa, in Lusaka, where this gadget works as a laser. The gadget is inserted into a septic tank or a pit on-site system and it is able to get the dimensions of the interior of that system. Now, this would have been normally very, very difficult to do, and a lot of times we struggle with this. We don't know what size the containment is, what shape it is, and so on. But this is able to do that. And that information is then able to be plotted, like you can see on the left. And we can get this information for the city, and that helps in the planning of the improvements to the on-site systems, as well as to plan the emptying and transportation of the sludge. And this has been used in Lusaka. The FSM tracker, this was again developed by someone in partner in India, where the tankers which are using the fecal sludge transportation, they're able to register, and you know where exactly they emptied, where they are taking it, who's the tanker, and things like that. And there is an FSM toolbox which has been developed with support from the Bill and Melinda Gates Foundation, which has got many, many tools which are all related to the fecal sludge management, right from the containment to the transport, the emptying, treatment, and reuse. So these are all freely available tools. This is a tracking tool which actually works with the desludging truck having a GPS, geographical positioning system, which then transmits to a centralized location, and we can see where the truck is going and things like that. And in Malaysia, in the utility I work for, they actually implemented this, and they had an enhancement where there was an additional sensor placed on the pump in the tanker, so that you could actually not only see the position of the tanker, but you could see when the pump was switched on and when was it switched off. So initially, the purpose of this was to prevent abuse of the tanker by the workers, where they could use the tanker for unauthorized emptying or unauthorized disposal of the collected sludge. But later, they found that the information that's being collected could also be used for routing of the tankers, and also to measure efficiencies of the team and to benchmark productivity. So the same information that was being collected can now serve more purposes. This is an interesting development which was developed in Dakar in Senegal by ONAS, which is a sanitation agency there. So they rolled out an app-based system which is used by people to call for emptying service. And when they call, the call actually routes through a call center and goes to the nearest tanker which is available. This works on a Uber model, Uber e-hailing model. And then the tankers are able to submit a bid. How much are they going to charge for emptying from this particular house? And that the system is able to assess and evaluate and select the best service provider, and then communicate with the house owner that this is the service provider for you, and then the work is done. And then there is again feedback after the work has been done. So through the system, the cost of carrying out emptying has been reduced through this healthy competition that has been introduced. And secondly, tankers who are unlicensed and who are running wild by discharging the fecal sludge everywhere, they were now in a more controlled situation, and where they take the sludge to a proper treatment facility, that could be monitored. And also there was a data collection possibility where these tankers, as they visit the site, they also collect information about the house, the containment, and the volume emptied, and things like that. Now, this is another model which it has not been done yet, but there's a proposal. So it's a Groupon model. If you know what is Groupon, it actually relies on the efficiency of a group purchase. So if we could do a zonal emptying regime for a city and divide the city into various zones and say, okay, now we are offering emptying service in this particular zone at a discounted price. And anyone who takes advantage of that enjoys the discount. So this might be possible through the online technologies which are now in app form. So again, that's not been tried, but this is an idea which I have also proposed somewhere. Now, for the benefits for the on-site systems are also similar, but a lot of times the on-site systems, they are at a very basic level. They are still in the primacy, and so their concerns are more to get things started and to get some private sector involvement, but not so much to improve efficiencies or to improve customer. Yeah, it could be partly, but basically I think they are at a much more basic level of benefits, but they are quite similar, and eventually this benefits will be similar. Now, as we can see, the need to manage sanitation, this is a worldwide thrust, and to do it efficiently will drive the transformation, and digital technology will offer the means. And the community expectations and demands are increasing day by day. And while the infrastructure that is being used is aging also day by day. And all these mean that business as usual cannot be an option anymore. And we have to use every possible tool to improve the efficiencies that we can achieve. So is the technology the solution? So in my opinion, and also in my experience, I find that the technology is the easy part. So getting the tool, getting that analysis tool for the digital transformation. That seems to be the easy part. Data could be a big challenge. Getting the correct data, getting a complete data, getting a reliable data on an ongoing basis. That will be a very big challenge. And if the data is not good, your decision is not good. And the requirements, you need to have people who really understand what they're trying to do and what is the transformation that they want to achieve. And that will then drive their requirements, and that will then drive what data they require or have and what analysis they want to do. And of course, this is an incremental thing that you go improving as you go along. So this is something not to be neglected, that we cannot have a very sophisticated tool when we do not have the people and we do not have the data to which can complement that. So some cautions that I think we need to look for. There are some pitfalls that could potentially happen. A lot of times the utilities or the local bodies, they don't know much about this particular topic, and they end up with very high-tech systems, but do not have the capacity or the data to match. And then it becomes a white elephant. There is also the danger of the black box. So people consider this is a plug and play, and I just put in some data and the answer is going to come out without really understanding what's going on. Again, this does not help in sustainability. And if the transformation is not driven, by a demand from the users, and there is no ownership from the user, and there is no readiness to adapt, then what happens is that after the initial installation, after the initial euphoria, you find things start going back to normal, and they start finding fault and saying, oh, this does not work as we thought, and this does not really suit us, So that again means that it will not be sustainable anymore. One of the experience I had was also, we had a very sophisticated system installed and people were asked to input a lot of data into that system, which they did over the years, but nothing was being done with this data. So after a while, they found that they could not really find a reason why were they putting in so much time and effort to input this data when it did not seem to be helping anyone. Least of all, they were not able to see. So one of the things to do is also that the user, must be able to see some results from what he's doing. So the data that he's inputting, it must benefit him in some way. Otherwise, he starts putting in garbage, so you get garbage in and garbage out. And finally, I think because of the affordability and so on, it is very good if we can start this based on the capacity of the people, and also in very small incremental steps. So people have time to buy in, people have time to appreciate, people have time to tweak the system, and then get the maximum out of that. So here in digital transformation, I think this transformation is the key word. So the digital is basically only the technology which enables the transformation. So initially, I think the people who are involved must have a demand, must have a desire for the transformation. And then the digital tools help them to move along in the journey. And generally, the institutional setup has a big role to play. And if you have a big utility company, for example, that is able to adapt this much easier because they have good financial capabilities, and they're also likely to have expertise which is able to drive the change. Unfortunately, the majority of the sanitation, especially the on-site sanitation, is dispersed. And this is being managed at the local authority level, where the resources are very minimum, capacity is also very low, and usually the drive is not there. There could be exceptions, but the majority of them. So this makes the transformation difficult for them. So this is where the problem comes. And wherever things have happened, which I've showed earlier, has been done because some managing utility has been set up. When the managing utility is set up, they're able to get the resources and have the drive and capability to drive the change. In some instances, technical assistance cells funded by government or some aid agencies, donor agencies, those have been drivers of change. In the case of India and Africa and also many other countries, you find agencies like USAID or Bill and Melinda Gates. These people have been driving change through some systems which have been developed and given to the utilities. So what can we do? What can we do for the local authorities? So I think what can be done in the case of some states in India, the state governments have actually set up kind of a state level agency. It could be like a utility, which is then able to work with the local authorities to provide a better service through various transformative technologies. Or it could be a technical assistance unit. So this could also be set up at the state level, and they would be the one providing the assistance to the local authorities. Secondly, the local authorities could make use of technologies which have already been developed by other local authorities or through these programs by donor agencies and so on. Twinning or mentoring between local authorities could also be a possible way out, where those who are a little bit more advanced could be hand-holding those which are less advanced. And system providers, people who are providing these digital systems, they could be helping the local authorities to approach this in a much more incremental way, taking baby steps and holding their hands and getting them into that, understanding the systems and then moving them on to sustainability. So this could be the roadmap for local authorities or utilities to move towards this digital transformation journey and the goal, right? So I think that's the end of my presentation. So I would stop here and thank you very much.
Thank you very much, Dorai. I'm sorry, but it appears that the Q&A box is not working. So participants, I encourage you to ask your questions, please, at the chat box instead of the Q&A box. If there are any questions for Dorai. Oh, there is one question now. It seems that the Q&A box is now working. How much would digital transformation cost? Dorai.
Well, I mean, this is a loaded question, right? So it depends on what you want to do. So things like very simple systems, like an app, for example, that could be already available off the shelf. For example, has been developed for other local bodies, so that could be easy for you to get. But then, if you want to go for more sophisticated systems, like a early warning system that we have installed, for example. So this would vary from place to place, depending on the number of sensors that you want. And then again, you need a centralized control system which receives the information and analyzes and so on. So I think it is not a question of how much it costs, but what do you want to do with it, and going in an incremental manner, starting with the very basic things that you could do, and then moving on, according to your affordability and also according to your organization's capacity. And you would find that the benefits, if you try to calculate in terms of dollars and cents, that may be a bit difficult, but a lot of the benefits are intangible, and you will find workflows become much easier, and your work itself becomes much more systematic because you have now gone on to a digital mode of working. Right?
Okay, second question. Thank you, Dorai. What is your opinion in applying industry revolution, big data analytics, and artificial intelligence in water and wastewater industry? This is from Zubat.
Yes, I think that is the end game. So you find that many industries and even utilities, if you look at power utilities, for example, telecommunications, they have already gone to that level. But the water and sanitation sector tends to lag behind because, like I told you, the reasons are that they are not very profitable, compared to these power utilities, for example, or for telecommunications. Water utilities and sanitation, particularly, they are not profitable. So they cannot think of very, high-end solutions like artificial intelligence, for example. But there's also a possibility that as time goes, many of these become much more affordable. because of the economics of scale. And there could be some systems which become affordable to these utilities as well.
So quite a number of questions on affordability and another question on ROI. What is the ROI that we can observe from this digitalization?
Yeah, I think I answered that. So it is difficult to calculate that ROI in that way, in a traditional way. That the benefits are going to be in the form of very many intangible benefits that the company and the customers and the workers would be experiencing, not so much in terms of dollars and cents.
Okay. A quick question. What is GIGO? I guess that's garbage in, garbage out, right?
Yeah, that's right. Yes.
Another question. What are the digital ways and means you think are good for collecting data from the field? And are these cost effective and easy for users?
Yeah. So a lot of the apps which have been developed for data collection have to be done through surveys. So now you need to make a call. Do you want to go out to the city and collect all the information in one go? Or you could start with some priority areas. And then as service is provided, like the emptying service providers, they collect data as they go along. So each time they go to a house, they also collect data from there. So it's a gradual populating of the database. So these are two ways, depending on how you want to do it. Big bang, then it costs a lot of money and you get all the information in one go. And the updating is done from time to time. So this is information for on-site systems. But when you come to systems like sewage systems, getting information on underground pipelines is not that easy. So this is where you have to go for a CCTV, and that's very expensive. And in my time in my utility, we started doing what we call profiling. So we CCTV section, and we think that the remaining area in that vicinity will have a similar condition. So we assume some things and we do some data collection and we do some assumptions. So from there we get a profile, and this gets cleaned up as you go along. As some problem comes up, you get more data from there. Because cost of collecting underground data is not so easy, not so cheap.
Another question, what was the turning point of the city which could be considered as the driving force to water and sanitation services towards digitalization?
Yeah, I think if your city is in the beginning stages of sanitation, for example, so there are very basic things that you must do to make that service available, make the service available to your people, and make the service affordable to your people. So for that purpose, this is just to start up, because a lot of times sanitation is non-existent. It's based on demand, but you want to go to the next step of making it the appropriate service. And to do that, you may need some basic level of digitization, which will help you to reduce the cost to an affordable level, which can then take off from there. Then as you go for efficiencies and try to make the system much better, try to have the service much more refined, then you may need to invest a little more. But that will be the starting point, I think.
Okay, Dora, there's quite a number of open questions still. I encourage you to respond to them in the Q&A box, as well as there are some in the chat box as well. Sure. Okay. But I'd like to end the session, the Q&A session for you at this point, because we need to proceed to our next speaker. And our next speaker is Jörg Gebhardt. Jörg is founder and managing director of BlueX Treatment Plant Optimization, which is part of Xylem. It is actually known as Aquatune, and it's coming out of Germany. Jörg is a PhD, of course, has a PhD in physics. I did not pass physics, I think. That's why I became a lawyer. From the Physical Institute of the University of Cologne. He also has a Bachelor of Science in Physics from the same university. Dr. Jörg, please, floor is yours.
Okay, thank you, Mai. Thank you for the introduction. And thank you, Dora, for this excellent talk. Really very interesting, and you very nicely showed that there's much data that exists, and the sources of data and how this can be used. This was excellent presentation, and I would like to seamlessly extend to that and show you just one more example how you can make use of those big data, turn it into information, and turn it into value and benefit for our customers and clients. So what I would like to talk about is about using artificial intelligence to build real-time decision support systems for the operation of water and wastewater treatment plants. Before I do this, I would like to give you a little bit of historical background, because AI is around since many years. What you see here is the beginning of the 90s. You can see me here when I met Professor Zadeh, who was the inventor of fuzzy logic. In the beginning of the 90s in Europe, and especially in Germany, we had what I call the fuzzy wave. So fuzzy logic and the application of it was very popular. I even had a chance to explain fuzzy logic applications to our former Chancellor Helmut Kohl. Maybe you heard of him. And fuzzy logic was all around. And after that, interest decreased, and I was working in the industry and doing automation and SCADA systems. So I make a jump about 10 to 15 years later, when I founded the company Aquatune. That was in the year 2005. 1 year later, we received a high-tech prize, the so-called the Cyber One, for our business case and our business plan. So at that time, when I founded the company, there was nobody who was talking about fuzzy logic anymore. Nobody was talking about artificial intelligence. And we started visiting wastewater treatment plants and talking about artificial neural networks and genetical algorithms to them. And that was really weird. It was an exciting time, but it worked. We found some customers who were willing to do this adventure with us and do the first applications of artificial neural networks to the operation of wastewater treatment plants. Now, another jump of 15 years now to the current situation. The situation has changed very much because AI is now everywhere. I'm sorry that this is in German. This is the hour of the AI companies, and it shows how Google DeepMind, for example, and other big countries, they are taking everybody from the market who is able to do AI. So all the scientists and students are getting employed by the big companies because they know that that in AI in future the value is in the application of artificial intelligence. So situation has changed a lot, and Xylem, the company we joined, as Mai said in the introduction in March last year, also recognized that the digital realm is the area where you earn the money in the future. So we joined them, and now we are rolling out these applications worldwide. Before I start to explain how this works, I would like just to talk a little bit about the process. One of the processes that we are providing solutions to, and this is the process of the activated sludge plants. So that's the activated sludge process, the most commonly processed in the treatment of municipal wastewater. And you have a reactor where the biomass lives, and in order to do its job, you have to provide it with oxygen. The numbers here come from a big plant in Germany. It's the wastewater treatment plant of Hamburg, where we apply about 27 tons of oxygen to the reactor. Now you can calculate that about 6 to 7 tons of oxygen go into the biodegradation, into the elimination processes. The surplus oxygen is only about 172 kilograms. You can calculate that from a set point of 2 milligrams per liter multiplied by the reactor size. you get to this number. And now the question is, where does all the rest go? And the answer is it goes into the atmosphere and it is lost. So this is a very big number, and this here is a very big number. And the surplus oxygen is just a very tiny little value. It's only 172 kilograms. But this is the value, the parameter that is usually controlled by the automation and SCADA systems. And automation and SCADA systems are state of the art. And DO control, dissolved oxygen control, is the most commonly used control scheme. And if you control this, then the parameter that really is of interest to us, to the specific energy, so the kilowatt hours per kilogram of load that you need, this changes by more than an order of magnitude, and it's completely uncontrolled. So that's the result. So you see that this process in nature, it's very inefficient, and there's a lot of opportunity to improve this. Now, how do we do this? We do this by a three-tier approach. Tier one is, as we call it, turn on the lights. That's data collection and real-time alerts and the SCADA integration. So that's the point where the data sources are. Like Dora was talking about this, there are many sources. In our case, most of the data comes from online sensors and from laboratory samples. Then from the data, we create a digital twin, a model. We try to come up with a model. In our case, this is an artificial neural network. And the reason is that the learning or the design of the model is a machine-based process. It's not an explicitly designed system like, for example, fuzzy logic, where you have to design all the rules and the membership functions and all this. It's a machine-based process. A machine will learn the interdependencies of all those parameters that have an influence on the results of your elimination process. And once we got the digital copy, we can use an optimization strategy to make use of it and to generate the benefit. Now the model, in our case, as I said, is an artificial neural network, and the name, which sounds a little bit like science fiction, it comes from an analogy to nature. We know in nature that the biological neurons, you can look at it in a very simplified way. You can look at it like being a CPU with a number of signals coming in, and with synaptics here where the signals are weighed, and here in the core there is some kind of calculation or reasoning being done, and then the result goes out via the axon to all the other neurons. And we map this to mathematics. We have a function here. They call it perceptron, but don't get confused by the terms. That's not important. Important is that you have several input functions that are weighed here at the synaptics inputs, and then you have a nonlinear transfer function, and it goes to the output. And this is how this neural network. This is the analogy. And here what I show you is an example from the real world, from a wastewater treatment plant. And you see the point is that we use signals from the real world. And as Dora absolutely correctly said, garbage in, garbage out, this is absolutely important that you make sure that these data are reliable. So we put a lot of our effort into designing algorithms that make sure that these data are plausible, because everybody knows that data from the real world has faults, it has gaps, it is incomplete, it has trendings and fluctuations and so on, and you have to deal with it. You have to make sure, because we are using a database system, we must make sure that the data is valid. And if that's the case, you can feed it to such a neural network, which is usually composed of several layers of neurons. The blue circles here represent our neurons. They are all interconnected. It has an input layer, an output layer, and one or more hidden layers. And when all those synaptic values are configured through the learning process in the right way, then the model will give you predictions or mappings of the target values. And the target parameters could be degradation rates, or effluent concentrations, or energy efficiency, or whatever is of interest in our process. So the principle is you have causes, and the model maps those causes to effects. That's the principle, and that works. It works always when you have a process with causality, and most of our technical or biochemical processes are such processes that have some causality in it. Now, once we got these models, how can we use them to help the operators to operate their plant? Because the operation of a wastewater treatment plant is a very challenging task, much more challenging than, for example, the operation of a chemical plant, where you have one point of optimum operation and then your product is produced constantly. In a wastewater treatment plant, you have to changes between dry weather conditions, like, for example, now we have pretty dry weather here in Germany at the moment. Then usually they don't have any problems to comply to their legal binding values in the effluents. But on the other side, they have stormy weather conditions where they go into overload. And overload means they receive more load in terms of chemical oxygen demand and nitrogen coming into the plant than they can eliminate per hour. And the consequence of this is rising concentrations. So the concentrations will approach their limiting values, and the operators are in troubles, and then they have to make real-time decisions, and that's where we want to support them. This can be done. This is explained in this slide here. How can AI help? Now, you see, you have a real plant, and in our case, this is a conventional activated sludge plant with an upstream denitrification and nitrification and final settler. But this could be any technical process. It could also be a coagulant reactor in a drinking water treatment, or it could be an anaerobic reactor or a biogas reactor. It doesn't matter. As long as it's a technical process, it has some input data and some output data. And there are some input data that you cannot influence, like, for example, the incoming loads or temperature or the flow of water. You cannot influence that. But on the other side, you have the set points of your automation system. You have to decide how to adjust the aeration intensity, how to adjust the recirculation intensity, for example, for the denitrification, how to adjust the dosing of precipitants, flocculants, and so on. And if you do good decisions here, then you will achieve your targets in the effluent data. But this is very complex and challenging, as I said, because there's many parameters that are influencing your process, and they are all interdependent in a nonlinear way. And additionally, you have high lag times. So if you adjust the aeration here, you will see the result in the effluent many hours later, because it can be the hydraulic retention times in such a process can be as high as 20, 25 hours. So that's very hard to control. And students of control theory, they really hate lag times, because it's really difficult to cope with that. Usual conventional control is always feedback control. That means you have to wait. You have to wait till you can measure the result at the output of your process, and then react. But the reaction comes too late, because the input situation probably has changed fundamentally. Now we try to bypass these lag times by making use of a model. And in our case, it's an artificial neural network. It could also be a physical model, like, for example, activated sludge model or something. But we chose this approach because the machine can do the learning for us, and the model gives you an answer at once. So you apply the same input values to the simulation as you do to the real plant, And then the model will tell you some predictions of chemical oxygen demand, nitrogen concentrations, phosphorus concentrations in the effluent, and you can react to the predictions. And by this, you can bypass the lag times, and we call these feed-forward control. And you can use this in order to optimize the operation of the plant. And this here is an example of some strategies to apply we use. I won't go to all the details. The most important question on this slide is which parameter is limiting the success? That's the most important question you have to answer if you want to optimize something. Because only there where you have a limitation, there it's worthwhile to change something. For example, if you find that the oxygen is limiting your success, then you simply increase the aeration intensity, and then you can improve your elimination. But to our experience, most of the plants, if not all of the plants that we've seen so far, and this is more than 100 plants, oxygen usually is not the limiting factor. Because of DO control, you're always in a saturation. So if you have a stormy weather event and concentrations in the effluent are going up, it doesn't help to increase the aeration. On the contrary, it is counterproductive because you have highly oxygen saturated water that you are recirculating into your denitrification, and they're decreasing the denitrification capability, and that in a situation when you desperately are in need of denitrification capacity. So that's one example how these optimization strategies are done, and it's basically exactly the same as the human operators do when they are operating the plant, because they also do a model-based approach. And the model, they have it in their guts. You know, they know that when they have a stormy weather event, they need to increase the aeration, of course. But the level of precision is much higher if you have some models available that tell you that give you predictions, and you can react to prediction. And so we found that on average, for example, in a wastewater treatment plant of Cologne, a big German city, which is my hometown, they have a wastewater treatment plant with 1.3 million people equivalents. And there we found that on average, our system switches 1.5 hours earlier back to reducing aeration and switching off swing zones to improve the denitrification and to improve the elimination of total nitrogen. The system has a logical module that we call load detection that takes several parameters to get an estimation whether the system is in load mode, when there's an overload, and then we switched our traffic sign to red, and we switched to the load strategy. And if the load detection says everything is fine, we have low loads coming into the plant, we switch the traffic sign to green and switch to the saving strategy, where we try to save as much energy and chemicals as possible. Now, what do we deliver to the plant? Where does the software live? We deliver a standard industrial PC. Most of the time it is delivered by us, but the client can also provide it by himself. And this is a plant, for example, I think that's the wastewater treatment plant of Trier here in Germany. And we have approximately 200 inputs, mostly analog inputs that we use to feed our models, and approximately 50 outputs that go to a graphical user interface to communicate to the client. And this is just one example of a graphical user interface. The design of this depends highly on the client, how the client is used to design such user interfaces. And I won't go into the details here for timing, just to give you a quick impression of how this looks here are some input values. Here you have the values, how the 15 lanes of or 15 parallel treatment tanks are adjusted. And here you have the predictions and some display of power consumption. Another example is monitoring systems, where we use artificial neural networks for as what we call soft sensors or virtual analyzers. You see here green curves, which are real measurements, real analyzers, and blue curves, which are virtual measurements. And for example, here in that case, you see a deviation, and where the physical measurement is constant, and our virtual measurement is increasing and then coming down, and then they meet again. And here in that case, for example, I would have a higher trust in the virtual measurements, and that's also what the clients find, that the virtual measurements are much more robust than the physical measurements. Now, at the one of the key performance indicators that we are using, as I said, is the specific energy consumption, and that's what I would like to show you here. The data is coming from a North German plant called Cuxhaven. I have a case study which I will show you in a couple of minutes, and you see the kilowatt hours that we have to apply to eliminate 1 kilogram of load is varying very strongly. The average is about 0.5, but it can go up to 5 or even more. That's before optimization, using just DO control. Now here you see these peaks of excessive energy consumption. And after optimization, we started here in August 2017. You see that those peaks are nearly gone. It's not a perfect straight line. That's really challenging, but it's the variations have reduced significantly, and the baseline has come down for more than 25%. So, and this translates into a saving of 330,000 euros in the case of this treatment plant of Cuxhaven, where we did the energy optimization for 5 parallel biological tanks. We built models of the carbon, nitrogen, and phosphorus elimination processes, and we calculate the best set points for the aerators and for the recirculations and so on. And another thing that we have, another specialty we have here, is that they didn't have online measurements in the influence, which is a very common case in medium-sized or smaller-sized plants. And we compensated for that by creating a virtual analyzer. We use artificial neural networks to calculate estimated incoming carbon, nitrogen, and phosphorus concentrations and loads. And so since we applied this system here, they didn't have any situations of breaking the compliance of their values. Another case study, just to show you a little bit of examples, what you can do with AI in water and wastewater area, is the anaerobic treatment plant in Eisenhüttenstadt, which is a treatment plant which sits behind a very big paper mill. And paper mills produce a lot of chemical oxygen demand, but they don't produce nitrogen or phosphorus. So you have to dose this into the reactor tanks, because the biomass, of course, needs not only carbon, it also needs some nitrogen and phosphorus to grow and to live. And so you have the problem here is the dosing. And here it's not about energy saving, it's more about stabilizing the biomass, because this is a much more sensitive process, and it's not so well understood as the activated sludge plant, which is a very robust and well understood process. So the main objective here is to operate the reactor in a way that they don't lose sludge, and that because that's very expensive if they have to purchase new biomass. And yeah, what we did was we built models of the COD elimination process and also of the gas production process. And then we calculated the optimized set points for the dosings, but also for the hydrolysis, which is another critical step in anaerobic treatment. So this is another example, a successful example of the application of artificial intelligence. And the third and last example that I wanted to show you is an example in a drinking water distribution. This is the city of Trier here in Germany. And they are providing the drinking water to the city. And they're using water from a well field, but also water from a big reservoir. And they have lots of renewable energies like photovoltaic. They have turbines and so on. And they want to make maximum use of this. And now they have pumping stations that pump the water into high-level tanks, elevated tanks, from where the water flows into the consumption zones. And those tanks with water are in fact a storage of energy, like a battery. You can think of them like a battery, because water at a high elevation contains a lot of energy. So we use those tanks, we manage the levels of the tanks by operating the pumping stations to decouple the profile of consumption, which is determined by the public, by the people in the municipality, and their behavior, and the profile of availability of renewable energy, because they want to draw as little energy as possible from the grid. And so to decouple those two profiles, you need storage. And that's the same like in the renewable energies in general, that the problem that we face is that the wind and photovoltaic are available at times which do not necessarily correspond to the times of the maximum usage of the energy. So what we need is storage capacity. In the case of drinking water distribution, these are the elevated tanks that contain the water. And so we were able to improve their use of renewable energies significantly, and we give them 24 hours predictions with 15 minutes of time resolution about the consumption and the different consumption zones, so that they can adjust to this perfectly. And this is just another example of the application of AI, and I really hope I was able to explain to you some basic strategies, how this can be used and how we can make maximum use of the available data. And now I'm looking forward to taking your questions.
Thank you, Jörg.
You're welcome.
You mentioned in one of the case studies that there was a savings of 300,000 euro.
That's right.
How large was that plant in terms of volume?
Yeah, good question. The question is excellent, because the saving corresponds directly to the size of the plant. So in that case, it's I think it was 400,000 people equivalents. So that's the measure that we use here. We have, when we look at plants like Cologne or Hamburg, they have a return on invest of significantly smaller than 1 year. It's only a couple of months until they get the return on invest, because of the big savings and of the big saving potential.
Can you explain a little bit? Because in the case of Malaysia, the sewerage, the whole sanitation utility is separate from the water side. In Germany, is it similar, or is it together?
You have both systems. I don't know the exact distribution, but you have both systems. You have mixed sewers, and you also have separate sewers. But the point that I was talking about is the treatment itself. And in the treatment, the situation is very much the same about the savings, because that's only depend on the way you do the operation of the plant. But we also apply those methods to the sewer network. In that case, we would call it Blue X water networks. And the combination of both brings another synergy or benefit, because then we are able to reduce the maximum flow to the operations, which brings us another factor that makes life easier and makes it easier to comply to the legal limits.
There's a question for you. Is there any implementation of AI in municipal wastewater treatment? The distribution of water using AI is fascinating. Is it being tried anywhere else? This is from Ashok Natarajan of India.
Yeah, thank you for that question. Yeah, we have many installations here in Germany, since we are doing that since 15 years. We have some installations in Switzerland and in the Netherlands. And we are starting now to do projects in the UK and in the US, and I'm in contact with the commercial teams or with our sales teams in Singapore for the Southeast Asian region, but we haven't done a project yet, so we are just starting.
Exploring. Okay, can you also, another question, can you give us an alternative software which can simulate models based on our own parameters?
An alternative software. Well, there are many tools around in the market for using ASM, activated sludge models, which are first principles based. So in contrast to the artificial neural networks, they use differential equations. So this is quite complex, and it's you have to calibrate this, and it's a big effort. Concerning artificial neural networks, I'm not aware of any competitors who do this. At least in Germany, we don't have one. I think in England there is a company called Innovise. I think they do a similar approach. But I'm not really aware of this. But if you're interested in tools for artificial neural networks, there are many tools around. Because, as I said, artificial intelligence is a big hype, and many people are now doing applications. So you find a lot of tools. One thing that I want to stress is, if an artificial neural network will always give you a prediction, no matter what you input there. So Dora said, and you said, garbage in, garbage out. You know, that principle is a universal principle. So you want to make sure whether your prediction is valid. And we developed a method we call security net. It's patented, and it supplies with each prediction we get a value that tells us how reliable this prediction is, and that depends on whether the network has seen this example or a similar example in the training database, or whether it hasn't seen it. So if you have an input situation that was not contained in the training base, the artificial neural network will give you an answer, but it could be way wrong. And so this is something you should make sure that you have reliable, valid predictions. That's very important.
A question from Dora. Have you used digital twins in sewage treatment plants or sewer network?
Yes, we have. There are many installations in the US. For example, in South Bend, which is the location where one of our sister companies called Mnet, they also belong to Xylem, and they did it in many places in the US, and we're definitely happy to provide you with information about this.
And one question, what is the difference between AI technology and automation of wastewater treatment plants? Are these two?
Well, good question. Yeah, there is no difference. We need the automation platform. Automation like sensors, PLCs, which are the workhorses that do the control and SCADA systems. This is something we do not touch. We just connect to it and set the AI application on top of this. So if you remember the excellent slide of Dora concerning the pyramid from the field to the top of the company, then you have the automation and SCADA system, and then one level higher, we have the AI application. And then on top of that, you have ERP systems like enterprise resource planning and this kind of system. So it's it doesn't replace anything. It's just an enhancement.
Okay. All right. That is it, I think. No other questions that are open at the moment. Just wanted to once again say that to both speakers, excellent presentations. If you can see also in the chat, both Dora and Jörg, there's quite a number of comments on the chat thanking you for excellent presentations, both of you. And we will share all of the presentations on our website. We've also put the link to the recording of this webinar if you wish to watch it again at the comforts of your time and home. I think at this point, I would like to thank you both. And we would like to go through a poll again, just to check whether we met your expectations. Participants, please join the poll. Thank you. Thank you. Thank you very much. So we have matched or met expectations, and for some of you, we have even exceeded it. So thank you once again to our excellent speakers for this afternoon. At this point, I'd like to call on Arjun Thapan, Chairman of Waterlinks, to do a wrap-up of the session today, as well as the whole series, because today is the last of the series of 5. Arjun, please.
Thanks very much, Mai. Let me first thank Dora and Jörg for very interesting, very educative, very useful presentations. I'm very tempted to say that we saved the best for the last, because this, as you know, is the last of a series of 5 webinars that we've had on the subject of digital transformation of Asia's urban water utilities. But I think it would probably be more appropriate for me to say that we saved perhaps the most important one, in a sense, for the last. You know, forgive me for putting on my development hat for a few moments, but
You're muted.
We have always, unfortunately, considered the sanitation part of water and sanitation as a bit of a laggard, and that sadly continues to hold true even today, when we have a pretty dismal sanitation coverage set of numbers for the Asia and the Pacific region particularly. And I think in that context, it's very important that we did discuss the adoption and the application of digital technologies in sanitation this afternoon. I think we have a long way to go. So I would look at this as an introductory kind of a discussion. And I think what I liked about both presentations were that they were made from the perspective of not just theorists, but practitioners. And I think that's very important for those of us who are trying to understand how to take this to the field and how to get utilities and local governments to apply these technologies for the greater good. Dora covered sewage systems and on-site systems. And of course, I mean, these vary in terms of which countries are using which kind of system. Malaysia, for example, where Dora and Martin are, has sewage systems in excess of 70% across the country. But Philippines, where Mai and I live, is hardly 7%. So I think obviously there's a huge range. I'd probably not be far wrong if I said that in South Asia, for example, India, Pakistan, Bangladesh, Sri Lanka, it's between 7 and 15% as well. So the entire process of FSM, which as Dora very nicely explained, lends itself quite nicely to the application of digital technologies. That's extremely interesting. And I think we need to take that forward and we need to take it to scale in a sense. But here I have a problem. And I think that problem is the kind of problem which most local governments and local utilities will tell you. And that is, how do I persuade people for an increase in tariff to cover the costs if I don't know what those costs are, and if I'm not quite sure as to whether the benefits are actually commensurate to the costs involved. So this is something that we really need to go into, because if you want this to take off in a big way, you really need a much better relationship between costs and benefits so that it can be clearly seen, and then monies can be raised, and there are plenty of ways of doing that. I mean, financial engineering is not the most serious problem we have. I think a much greater problem we have is in persuading people that this needs to be taken up. I'm so glad that Jorg spoke about wastewater treatment, but here again, I feel that perhaps we need to change our thinking, or at least our perspective a little bit. I'd like to consider this as more like water resource recovery facilities, because we're really looking at a whole range of resources embedded in what we call used water or wastewater. We can, of course, very simple, and it's happening in some parts of Asia as well, we can get lots of varieties of clean water after treatment for a variety of uses, whether it's industry or agriculture or commerce. We can get energy and biosolids from sludge, for instance, and we can get phosphorus to give us fertilizers. And all of these products, if you call, or byproducts, really have a very clear financial stream. But I think we need to add to this the economic benefits. There were some studies done some years ago now, and unfortunately they haven't been repeated, and I think they should, which kind of tell us as to what the public health and economic impacts of poor sanitation are countrywide. And if I remember right, anything between 5 to 7 or 8% of national GDP is the kind of impact of poor sanitation systems. And if we can shrink that by using digital technology to be more efficient in not only providing the existing cover of sanitation, but expanding that cover, then I think we'll be doing the communities we serve a much higher level of service. That's what we really need to be aiming for. So let me just leave you with those thoughts, but let me also again thank Dora and Jorg for very interesting presentations, and to everybody else who sat in this afternoon. I'd also like, since the last of this series, I'd like to thank Xylem, our partners, as well as my colleague, Mai Floor, who's ED of Waterlinks, for the great efforts that have been put in organizing this series and in thinking through the wonderful set of speakers who made it all who made it also very worthwhile. Thank you very much.
Thank you. Thank you.
Bye-bye. Thank you. Thank you.